Anyone who has not signed the attendance sheet, please pass it to the back. After you are done, you pass it to the back, the attendance sheet. So we will wait for another 2 to 3 minutes, then we will start. Pass it to the back. This row at the back, they have not signed. So everyone please download the .step file which I shared yesterday. So today we will be doing two-way FSI simulation. So we will also need, apart from fluent, the static structural or transient structural part. So for today's demonstration, I will show you steady state two-way FSI simulation. So for that we will basically need two modules. One is static structural, just drag and drop from this analysis systems list. And the other is the fluid flow fluent. And also in order to couple these two, we will be requiring system coupling, which is under component systems. So you drag and drop these three. So as we will be doing only steady state simulation right now, so I have chosen static structural. For pulsatile simulation, you will have to choose transient structural from the list. Like I am choosing yes, we will not be using the transient structural part for now, but yes, for the pulsatile simulation you will have to use this. So the first three like static structural, fluid flow and system coupling should be there on your screen. Just tell me once it is done. Then right click on the geometry in the static structural component and then choose import geometry and import the dot step file which I shared with you yesterday. So, first bring the static structural, fluid flow fluent and system coupling from the left hand side list and then import the geometry in the static structural component. Like right click, then select here in my case it is showing replace geometry, but in your case it will be showing import geometry, those who have not imported. So, right click, then select import geometry and then you choose that file. So, it will show a green tick once the file is imported. Then double click on models. So, system coupling is under this component. So, under this component systems you have, so you select system coupling, here it is. It is under component systems, not custom systems. Anyone yet to do up till this who has not completed? Opening, okay. Just tell me when this model is opened in the static structural part. So, just import the geometry and then open model. So, so just click on this geometry, then you will be able to see the geometry and then click on the plus sign over here. So, there are two bodies, one is the wall, means one is the solid domain, this one is for the solid domain and this is the fluid domain. So, since this is the static structural part is only for the solid domain, we will be suppressing this fluid domain. So, just right click on this and then click on suppress body. Right click on the fluid domain and then click on suppress body. So we will get only the wall over here. So just for the information, the diameter of our channel was 3.4 millimeter, and the thickness I have taken 0.1 d, that is 10% of the diameter, the wall thickness. It is having uniform wall thickness, yes, that is 0.34 millimeter. Then click on mesh and click on right click on mesh and click on generate mesh. So the mesh is quite coarse, so we will again be doing body sizing over here. If you can't follow, just tell me to stop. Wall thickness I have taken 10% of the diameter, means 0.34 millimeter. So I forgot to mention one part, so just close the model. First we need to specify the properties like the Young's modulus and the Poisson ratio of the wall. Those two are the very important parameters for the deformable wall simulation. So just close the model once the meshing is done. So we will need to refine the mesh. So I will again open the model, but first let me show you how to prescribe the Young's modulus and Poisson ratio. So double click on this engineering data. In the static structural there is engineering data, just double click on that. Just click the plus sign left to that. So you can see that the Young's modulus by default it is 2 into 10 to the power 11, which is almost like rigid. So it is very high Young's modulus, that is almost rigid. So we need to decrease this. So today in the class Suman sir showed in the presentation which he showed, he has taken 500 kilopascal. So that same Young's modulus will be prescribing over here. So it actually in real physiological scenario it varies from around 1300 kilopascal to around 2800 around 300 kilopascal to around 2800 kilopascal, in that range. Exact range I am not sure, but in that range. So for the time being you just take 500 kilopascal, so 500,000. $500 kilopascal means 500,000 pascal, and change the Poisson ratio to be 0.4 to 0.45. 45. Anything you can take, the Poisson ratio will not matter much, means the results will not matter much. The main parameter is the Young's modulus. All other parameters you can keep as it is, because if you have checked the if you have looked into the theory classes, then you will know that only the Young's modulus is the main parameter. All other parameters are not important for our case. So don't so close the engineering data from here, like this tab you close, do not close it from here, then it will close the Ansys, the entire file will close. So close it from here, engineering data. And in between please save it, because if anyone can't follow, then please stop me in between. So again double click on this model and click on yes. So we have not completed the modeling part, so we will have to refine the mesh and give the boundary conditions and all. So this was the mesh which we previously created. So now we will be doing body sizing. So just same as before, right click, insert sizing. Then as I said that this is in the top, this 4 green color boxes, this is for the edge vertex selection, this is for edge selection, this is for face, and this is for body selection. Just select the body and click on the entire body, and here click on apply beside geometry. Change the element size to 0.0002. You can play with it, but yes, for now you can keep this 0.0002, and then again right click on mesh and click on generate mesh. So now our mesh looks fine. Now we will have to apply the boundary condition. So So for this simulation, at the outlet, just like previous, we will be considering 0 pressure, like 0 gauge pressure. So when there is no pressure on the vessel wall, then there the deformation will be 0. So here deformation is 0. But if we only prescribe on this wall the deformation to be 0, then Ansys will not be able to complete the simulation. Ansys needs another boundary condition. So if you look at the theory of so yesterday Suman sir talked, I think, about the analytical solution of the deformable wall microchannel. So the deformation profile actually looks like this. Like if this is the wall, so the wall will be looking something like this. So at the inlet there will be maximum deformation, and at the outlet there will be minimum deformation, because at the inlet the pressure is more and at the outlet the pressure is less. So but for Ansys, since we require another boundary condition, so we will be forcefully prescribing in this wall the deformation to be equal to 0, which is actually not correct. So after simulation in Ansys, you will be finding, like, if this is the original profile, so this is the correct profile. So in Ansys will give you result something like this. So here like this is the wall, and then the wall suddenly achieve that height, and then so near the inlet the results which we will be getting will not be correct, but away from the inlet the results will be correct. So like I said that in real physiological scenario, the outlet pressure is not 0, it has some value, and that depends upon the systolic and diastolic pressure. But in that case also we will have to forcefully prescribe deformation to be 0, because we do not know the actual deformation at the wall. If we would have known the actual deformation, then we could have prescribed that value. But from the real from any of the medical data, we will not be able to get the actual deformation at that point, like how much the wall is expanding. That value we will not be able to get using the MRI data, phase contrast MRI data. So for both the cases we will have to forcefully impose this 0 deformation boundary condition. So in that case like towards the inlet and towards the means near the inlet and near the outlet, the results which we will be getting will not be correct. In between the results will be correct, because we are forcefully imposing that boundary condition. So if we could know the value of deformation at the inlet and the outlet from any of the medical data, then we could have prescribed that deformation. But since we do not know, we will assume it to be, means not assume, like we will forcefully give it 0, and but so the results in this region and this region will not be correct. In this region it will be perfectly fine. Yes, so for prescribing that 0 deformation, we will be just right click on the static structure and then click on insert and then click on fixed support. So we are fixing this, fixing the two like two faces, so that the deformation is 0 over that two faces. So just select the two faces over here, like this face you select and the outlet face you select. So just use control and then select, otherwise the first selection will go. Select the first face, then click on control and then select the second face. So then click on apply. So just check whether there is blue colored this thing coming, so that means your selection is proper. So again I am saying that deformation 0 is not the correct boundary condition. We are forcefully imposing that in Ansys. So our results towards the inlet and towards the outlet will not be correct. In between the results will be correct. So actually the profile will take a sudden jump and the inlet, and then like at the inlet it will be 0, but just a little bit far from the inlet it will take that height, and then so after simulation you can see the result. Now this is only for the solid domain, but we need to couple the solid and fluid part. So for that we need another boundary condition, like just right click on the static structural, click on insert and then click on fluid solid interface. Like here we will have to select the interface between the fluid and the solid. So the interface is actually the inner wall of the vessel. So this is the inner wall, not this one, this is the inner wall. So just click on this and see it very carefully, click on extend, just click on this like inner wall, then click on extend over here in the top right corner and then click on limits. So you can see that the entire inner wall is getting selected. You will not have to press the control key and select. So what is the advantage of using this extend and limits? So this is a perfectly cylindrical channel. So you can manually select one face, then press the control key and select the other face. But in case of a complicated geometry, you will not be able to select all the faces manually. So for that you need to just click on one of the inner walls and then click on extend and then limits. So it will select automatically the entire inner region. So again I am showing, just click one. So you can see that one of the faces it is getting selected and the other one is not getting selected. So then just click on extend and the limits. Okay, then click on apply. So this extend limit part is very important in case of complex geometry. There you will not be able to manually select the internal lumen as a whole. So our this part is done. Now we will add some results from here, like the results we will not get here, but we will add so that we can see them in future. So right click on this solution, then click on insert, and we need to see the deformation, like this thing which I have showed on the board. So select total deformation. Again right click on solution, click insert, and we also need to see the stress. So click on stress and click on equivalent von Mises stress. So you can also choose other things like directional deformation and all. So here I have chosen 3: total deformation, equivalent stress, and directional deformation. So do not click on solve. You do not have to solve it now, because this is not complete. We will have to couple it with the fluid flow fluent. Just do not click on solve now. Tell me once this is done. And in between, if you have any doubt, you can ask me. So that after the everything is completed, we will. Oh, like here, total deformation, equivalent stress, and directional deformation. Solution information. No, you don't have to give anything in solution information. So anybody, so in anyone's simulation, is this showing in red, the solution information? Have you given the fixed support and fluid solid interface boundary condition?
It's only because of we have given us happy solve. By mistakenly we have clicked the solve. That's why click the solve. That's why.
Oh, okay. So you can keep it like that. I don't think it will cause a problem.
It's just the normal.
Yes.
This is what solution we will be asking.
Yes.
I don't think so it will going to hamper anything.
So after this is done, you close this. And right click on this setup and then click on update. Do not click update on solution because everything is not given. So just click on this setup and click on update. So you can see the progress from here. So everybody completed the static structural part till now, whatever I have done. So just like yesterday, similar thing we will have to do in the fluid flow fluent. So you don't have to import the geometry again, just drag and drop it from here. So just click on the geometry in the static structural and then drag and drop to the fluid flow fluent geometry. So it will show a line, connecting line. So please save it in between because everything will go. So double click on this mesh and do the meshing which I showed you yesterday, like body sizing and inflation layer. And also create named selection. So that part I am doing it very fast since you already know. I have shown it yesterday and day before yesterday. Geometry. Yes. No, it will direct to the geometry. Geometry should be directed to geometry only. So in the static structural part, we have suppressed the fluid domain, and for this part we will be suppressing the thickness, that is the solid domain. So just just click on this plus sign in the left of the geometry. So again, you can see two bodies have been created, one for the fluid and one for the solid domain. So here you suppress the solid domain. Right click and click on suppress body. So then click on mesh and click on generate. So after that we need to do body sizing. So right click on mesh, insert sizing, select the whole body and then click on apply. Select the element size to 0.0002. Click on mesh and click on generate. So I am doing this very fast because day before yesterday and yesterday I have showed the same thing. So, right click on mesh, click on insert and click on inflation. Choose the entire body, click on apply, select the, just control and select the two faces, the two walls, click on apply, choose the maximum number of layers to 6 and then click on generate. So, you can see that same thing like 6 inflation layers. So, now we will be doing the named selection. So, just click on this in this face. So, yes, this I will be choosing as inlet. So, just click on this, right click, create named selection and type inlet. Similarly, click on this, right click, create named selection, click on outlet and then select the two walls and right click and click on walls, create named selection, walls. So, you can see the 3 names created: inlet, outlet and walls. So, this thing it is similar to the previous yesterday and day before yesterday's class. So, I am just closing the mesh. So, again right click on this mesh and click on update. Has everybody completed? So, I am opening the setup. Setup also same as yesterday's class. So, select double precision and click on start. So, choose the model from SSTK omega, means change it from SSTK omega to laminar, then click on OK. Then same as before, just click on this materials, fluids and then air. Change the density, name, you can name or rename. So, rename and change the density and viscosity. So, keep the density to be 1060 kg per meter cube and the viscosity to be 0.004 Pascal second. So, click on change or create, yes, and then click on close. So, now we will have to add the boundary condition. Since we were not doing a pulsatile flow simulation, we at the inlet we will be prescribing uniform velocity of 0.12 meter per second. Viscosity is 0.004, means 4 into 10 to the power minus 3. So, double click on this inlet and change the velocity to be 0.12 meter per second. Then click on apply and then click on close. And outlet by default it is 0 pressure and wall it is no slip boundary condition. So, I am not clicking on those two. Now, the next step is different from the one which I showed yesterday and day before yesterday. So, up till this Hello? Hello? So just double click on this dynamic mesh. So just check this box and then click on create or edit in the bottom. Create or edit, there is an option. Yes. So we have in the named selection we have named the walls. So select the walls from here and then click on system coupling. In the named selection we have named the walls. So select the walls and then click on system coupling. Click on create and then click on close. So it will show like this, walls system coupling. This is for coupling with the solid domain, like we need to have dynamic meshing because of the deformation. So double click on this methods now. So let it be coupled. So do not change anything from here. Choose the default settings. Then click on initialization and initialize the solution. So dynamic meshing, did everyone complete dynamic meshing? So click on dynamic mesh, tick on that box, select create or edit, choose wall from the drop down menu and click on system coupling. So that part was only different from yesterday's simulation, rest all are same. Okay, let it be, yeah. So then click on run calculation. Do not calculate, just give the number of iterations to 1000, but I think you may or may not give, because anyway it will be overwritten by the system coupling, the third tab which we opened. Do not click on calculate, because we need to couple the till now the fluid and solid are not coupled, so we will have to couple that. So do not click on calculate. If you click on calculate, it will only do the fluid flow simulation.
While initialization it is showing that convergence tolerance.
It may be due to the meshing, maybe.
But we have not given the residual convergence tolerance to 10 power 6. It is 10 power 3 only.
No, this is not that same as that convergence tolerance. So this is something, yes, this is different.
For us it is not showing because we taken some different.
Okay, then it's good. So for this mesh, maybe. So you will have to play with the mesh. Like for only the fluid flow part, it worked fine, but maybe for this part it will not. But solution will anyhow converge, because the convergence criteria is very less, 10 to the power minus 3. So you can visualize this thing, but quantitatively it will not be correct. So just close this after that. So just check everything is like for the fluid flow, the geometry mesh and setup should show in green tick, and for the static structural, engineering data geometry model and setup should show in green tick. Just check that once, then we will proceed to the next step.
Here we have not changed anything about that autosave that we have done.
No, autosave is required for pulsatile flow simulation.
Here
For steady state, why is it required? For steady state, it is not. So, just click on this setup and then drag and drop the setup from here to the system coupling. Similarly, for the fluid flow, click on the setup and then drag and drop to the system coupling. So, just again click on this setup and click on update, like it is showing that update sign, click on update. Both the setup should be connected to the system coupling setup. Just click, drag and drop over there. And just right click and then click on update in both the setups. Yes. So, is it completed? Anybody who has not catched up? So, now double click on the system coupling setup and click on yes. So, it will show something like this only. So, click on this analysis settings and change the maximum iterations to 10. So, I think it will not take 5, it will be finished less. So, it's this number of iteration means the coupling between the solid and fluid, like from the solid the information is passed on to the fluid and from the fluid the information is passed on to the solid. So, that how many times it is being passed on, so that this is that number of iterations. So, I have checked, so you may need more. So, I have checked, it takes around 3 for this particular simulation. So, you will have to increase if the solution is not converged. So, it is better to take more, like 100 you can take. So, just see, you have two regions over here. One is the fluid solid interface, which we selected in the static structural part, and another one is the walls, which we selected in the fluid flow fluent part. So, just click on one of them, like fluid solid interface, then control and then click on another. So, it means select both of these, then right click and choose this option, create data transfer. So, you can see two data transfers are created. So, if I click on the first data transfer, so here the source is the static structural and the target is fluid flow fluent, means the information is being passed from the static structural to the fluent. And if you click on data transfer 2, here you can see that the information is being passed on from fluid flow fluent to static structural. So, it is two-way coupled. So, save this, otherwise it will, before running the simulation, save this. So now our setup is completed. So just click here, there is an update option, click on update. If you click on update, then the simulation will start. It will take some time, and in between you can ask me anything. Like now we don't have to do anything until we get the converged solution. So you can see the iterations over here, it will show up. So now it has not started yet, so it will take time. So if your Windows is blocking something, then click everything allow. So this is the first time I am running the simulation on my laptop, so all these things are coming. In your laptop it may or may not come. If you have performed the simulation before, then it may not come. Solver fail. Just check whether solver failure is occurring for everyone. Because I tried this simulation in my like lab PC, so it worked fine. So just check. So you can see that coupling iteration equal to 1, that means the first iteration. So both are not converged, static structural not converged, fluid flow fluent not yet converged. So once both are converged, then we will get the converged solution. So both of that has to converge, and then the system coupling also has to converge. So 3 convergence we will get. So it will take around 3 coupling iterations to get a converge, 3 to 4. In between, if you have any doubt, you can ask me. And everybody has signed the attendance sheet. So please pass the attendance sheet to 3 of them, those who have not signed. And I gave a sheet for new VSRC boys to sign. So where is that sheet? Anybody who has not yet signed the attendance sheet? So you can pass. Pawan, you can give it to them. So you can see for coupling iteration 1 is not yet converged, not yet converged. So 3. So your is finished. Okay. So let it finish in my laptop, then I can show you the results. Yes, yes. So this coupling iteration 1 means both way, means from fluid it is coming to solid, solid it is coming to fluid. So that thing. So that is overwritten by this. So that is not that important. So that the solver automatically takes.
So how many iterations that is taking from the?
We will not be able to know that.
You can do one thing, there in just below solution information, you can see there is written fluid flow fluent. If you click there, you will see the fluent just below solution information on the left.
Okay, okay.
सिस्टम कपलिंग के नीचे सॉल्यूशन में नीचे
আচ্ছা আচ্ছা এইটা Yes, so after 3 iteration it is showing converged. So close the system coupling from this tab, do not close it from here, it will close the entire thing. So let me just save and close. Then click on results in the static structural, those who have completed for them. Post processing of fluid flow simulations I have already shown, you can do same thing over here by clicking here, but I am showing that I am willing to show the deformation. Yes, so then click on total deformation. So there you can see the total deformation. So at the inlet we have forcefully prescribed zero displacement. So the wall you can see at the inlet. So it's just after the inlet it is taking a jump, means and then towards the outlet it is gradually decreasing. So this type of profile like 0 at the inlet and maximum just near to the inlet is because we have forcefully imposed the zero deformation boundary condition over there. So if we had known the actual deformation at the inlet, then we could have prescribed that. But since we do not know the actual deformation, so this is the best what we can do.
Is there any other way like you can describe another boundary condition so that
Like you can prescribe displacement boundary condition, like how much the wall is displacing, but since we do not have that data, means what will be the displacement at the two ends, so we are not prescribing that. You can also prescribe displacement boundary condition there. So this is the thing which I wanted to show, this deformed channel, which yesterday in theory class you have been taught. Yeah, analytically, yes. So that was for micro channel. So this is for micro channel, but the concept is same. So if you have completed this, just tell me if you have completed this part. because the FSI simulation basic thing is done.
Can you also show the fluid flow, but is it replaced with the
So, we will be able to see that using the contour plot, like just let me check. I have also not checked whether it will show the displaced thing or not. So, fluid flow, I think the deformation is not showing, but so in fluid flow the deformation is not showing. Just do anybody have the rigid wall like yesterday's simulation, steady state simulation result now? So, just check that what is the pressure difference at the inlet. So, the pressure at the inlet for the rigid wall should be more than that of the deformable wall, because at the outlet we are fixing 0 pressure. So, the pressure drop decreases with the increase in deformability. So, if the pressure drop has to decrease, the inlet pressure has to decrease. So, those who have the rigid wall simulation, just check whether the pressure in deformable this one and the is less than that of the deformable one.
how can you confirm that it's just coupled like
So, that can be confirmed using this by seeing the pressure, it should decrease. And one thing for confirmation is that if this would have not been coupled, then we would have not got this type of deformation, because it is the pressure of the fluid which is causing deformation. So, this is one way coupled for sure, but whether it is two way coupled or not, for that we will have to check the pressure. Like from the pressure, like the information has been successfully been transferred from the fluid flow fluent to the static structural. But whether the information has been transferred from the static structural to the fluid flow fluent, that can be validated using that pressure. So, just I want to check that. If anybody have the pressure like rigid wall simulation result of day before yesterday's. So, is it decreasing? Yes. So, what is the pressure for the rigid wall? How much what was it was like inlet minus outlet, if we do, how much it was coming? Outlet you can take 0, this small minus 10 to the power minus 2 is due to the numerical error. So, outlet you can assume to be 0, just do inlet minus outlet. Just let me check once. Oh, 100, okay. Yes, so that means it is so then we can confirm that it is two way couple, but this pressure they are showing for the undeformed geometry, means like we can't visualize it, but quantitatively we can get the value. So visualization can be done in static structural part, that is how it is deforming.
Have you plot any graph for deformation in structure?
Yes, we can plot. Like the quantitative value, how to get that I also do not know, but it is possible to get that I am know, but how you will get, you, I think you will have to play around. So did everyone complete this part? So then just close this. And yesterday I also shared with you a patient specific geometry of a carotid artery, and I am sharing now with you the, I forgot to share in the email, so I am now sharing with you the velocity. So I am just disconnecting this from here. And you will have to do pulsatile flow simulation in that geometry considering rigid wall, that FSI you will not have to do now. Just do the setup. So this is your now half an hour task. So you will have to do the setup, do not to run the simulation. Like yesterday's task I am giving for a patient specific condition, the geometry I am already providing, and the boundary condition like inflow velocity also I am providing. Yes. So yesterday I shared the geometry, so now I am sharing with you the bifurcating artery, BIF artery, something like that. So this I will not show it. So yesterday I have shown how to set up the pulsatile flow simulation. So you will have to edit the text file .txt file, save it in a proper place. Yes, so just now I have sent the text file .txt file, it is inflow.txt.
Yesterday you shared one file with the name of flow. That is not the same?
No, that was for the coronary artery. Like whatever we did till today, it was for the coronary artery case. But that is the patient specific carotid artery, and that inflow profile is also patient specific. So, which I shared. So flow profile I didn't share. So just now I have shared it with you. And geometry, I think the name is yes, this one. This is the name. So you just have to set up the pulsatile flow simulation. So you do not have to run it. Just show me the .txt file, how you have edited and where you have saved, and where you have like given the boundary condition. So at the outlet for the time being you can keep 0 pressure, but that is not the case. So pressure waveform I will share it with you. For now you can take 0 pressure. No, it is velocity.
Number of points 68.
That you will have to check in Excel. I forgot the number of points. Just copy paste that data in Excel and check how many number of points are there. So you'll have to count that 0 also. So 0 and
One is the top, no? So if you take 67, then one will be missing. 13 one, that will be 16.
so just let me check how many points are there. 67 or 68. So there are 67 points.
If you take it up to 67, then one is another one, a 0 point.
No, 0th point is 1. Like you count the number of rows. Like it's 67. So just tell me when the setup is completed. You don't have to run the simulation. No, click on system. So just do it once more. Okay, just then close. Yes, click on close. Yes, so now again create a window. So now choose 113. So did you like in the name selection you created two walls instead of one? No, I selected no, not in the solid part. In the fluid part. Extend.
In that both included it is showing two phases. The word.
But in the name selection it should come.
No, that's not.
You just click on configuration command. So just click on wall dynamic mesh. Just check whether walls is there or not. Just check the video once, like every step is same or not. Video recording. sheet which was here.